Okay, slight technical hiccup. My phone ran out of space to record video, so I had to go back and delete some stuff. But now we're back. Well, not that you guys realized the gap, but for me it was a bit of work. Okay, where were we? We're talking about finding distributions of kinetic energies of a gas. Okay, so the object of interest is this guy here, infinitesimal E times the number of particles with some particular energy. Okay, scribble that out. So I'll just write down here that dE and E is going to be GE FB, our Boltzmann distribution, right? This is a classical system still, dE. Okay, so we have the density of states, we have the Boltzmann distribution, and we have still our infinitesimal energy, which, plugging in our Boltzmann distribution, gives us A, G, E, E to the negative E divided by KT, dE. Okay, so far this should be familiar. Now, if we want the distribution of kinetic energies, we need the density of states. So we'll get to that from the relationship between kinetic energy and velocity. Right? So we know that kinetic energy is equal, I'll write KE, so we don't confuse it with Boltzmann's constant. So kinetic energy is equal to 1/2 mv squared, of course. And this we just invert, v squared equals 2e over m. And then we take the infinitesimal version of this. So dV equals 2me root under dE. Okay, so that should be pretty straightforward, right? And we know from before when we were talking about the relationship between velocities and density of states, so go back a lecture or two if you want to see why this is so. Remember I drew that little diagram with the shell. So our density of states, G of E, is equal to 4 pi n v squared, right? Where this is the number of particles. So we just carry through with our calculation and we get G E dE equals C, which is just some constant, 2e over m 2me square root under dE. Okay. So this is a little different than the way the book does it, but I think I do or I'd rather that I have a little bit of a clearer explanation. So, but if you don't get my explanation, then have a look at the book also, and maybe between the two of them, you'll understand it better. Okay. So now we want to get back to this n, right? So we have n e dE equals C prime, right? Some new constant, right? So we're combining this C and this A. M cubed 2e e to the negative E divided by KT dE. Okay? And we know that total number of particles is just the integral over all the different energies, particle number as a function of energy, right? That's just saying we're going to have some curve that's going to be number of particles given a particular energy, and if we want the total number of particles, we just do that integral. Okay. Now, the next thing we do is normalize that so we can find that constant C prime. So let's write everything out. And E dE equals pi KT 3/2. And this is us finding that normalization, which if we wanted to find that the normalization, we would just go back to that previous equation and do that integral and set it equal to 1, right? It's a Gaussian integral, but we know how to do those now. So to get this here, which is this is that C prime, a constant that sits out front, we do that integral, set it equal to 1, and then we get that C. Right? We just solve for this C, just like we do with wave functions, right? Wave functions and these things as well are all about probability. On the other hand, many things are similar. So that normalization procedure works more or less the same way. Okay. Continuing, we have square root e to the negative e kt dE. All right. So this is the distribution, right? This is the thing, right, that tells us how many particles have a particular energy in this gas. So we haven't said what the gas is, right? So this is for any gas, unless it's doing something really weird, which sometimes gases do weird things, and we'll talk maybe a little bit about that this class or the next one. Okay. So now finally what we were, well, maybe I'll just draw this to give you an idea. Right? This looks kind of like this. Right, where this is that N of E curve, and this is energy, right? It isn't exactly how it looks because I'm bad at drawing, but more or less. Okay. No, this isn't. Yeah, this is energy. This is number of particles, of course. Okay. So if we want to find the average energy, right? What's the most likely, or rather, what's the average, the mean particle energy? We do this in the same way that we calculate expectation values, because again, it's all about probability. Right, we've got our distribution here, here, and now we're just sticking in that E, right, to find the expectation value of that. So we do this integral plugging in all the constants, pi, kt, 3/2, under 2 pi, integral 0 to pi, dE, e to the 3/2, e to the negative e divided by kt equals 3/2 kt. So we get this really simple expression, right? All of that complicated math just gave us 3/2 kt. Now, if we want to make that plain, what's going on up here on this diagram, right? That expectation value of E, 3/2 kt, sort of right there, right? A little shifted off from the maximum, right? Because we're talking about the mean, not the median. The median would get us this guy here. And so that's going to be about halfway between kt and 2 kt. Okay. So this is a demonstration of what is called the equipartition theorem. So this is something that's valid classically. Things become more complicated when we talk about quantum mechanics, obviously. So the equipartition theorem says, in thermal equilibrium, each degree of freedom contributes 1/2 kT to the average energy per molecule. So now I'll write that down and then I'll talk about it. If you're looking for a good old movie to watch, it's totally mindless and just a bunch of action and weird science fiction stuff, go check out the movie Equilibrium. It's one of my favorites. It's about what's his face, Christian Bale, and it's the future, and people are outlawed from feeling emotions, and Christian Bale basically kills everybody. It's a really fun movie. So if you're stuck at home and you've watched every movie you have, maybe that's a good one to watch. Maybe I'll watch it today. Okay, so in thermal equilibrium, each degree of freedom contributes 1/2 kT to the average energy per molecule. Okay, so we have 3 degrees of freedom for this gas, right? So we have 3 times 1/2 kT, right, according to our equipartition theorem. So why should this be the case? Well, if you imagine you have a gas, all the particles are zooming around and bouncing off walls and occasionally bouncing into each other and interacting with each other. If we have that gas reach thermal equilibrium, that basically means that most of those particles have evened out their energy to some extent. You know, obviously there's still this distribution of energies, but they've essentially shared all of their energies to such an extent that each degree of freedom is sort of independent, right? And then this equipartition theorem tells us that we get a 1/2 kT contribution from each of those degrees of freedom. So if we trapped a gas in a 2D plane, which there are things that behave like that, like electrons bouncing around in a thin conductor or something like that, then we have a 2D gas and we would just have kT, right? We would only have 2 degrees of freedom, and therefore we would have 1/2 times 2, we would have kT, okay? So that's as much of classical statistics as I want to do, and now we're going to make the switch to quantum statistics. So the key difference between classical and quantum statistics is that we cannot label quantum particles. Okay,